My name is Christopher Meiklejohn, and I'm going to talk about C8DB, a geo-replicated conflict-free document database from Macrometa. Geo-distribution is challenging. If we consider ourselves a startup, let's say a mobile gaming startup, we may typically start by deploying our application into one data center, here as outlined by, say, the Amazon US West 2 region in Oregon. Now, the challenge here is that our mobile users of our application are located all over the world, and so not everybody has uniform latency and the same availability to reach the application. And so typically what we do is we geo-replicate our database into a number of regions of the world, which reduces the latency for users who are located in different parts of the world. And it also increases availability, so we're not reliant on one or two data centers to keep our system running for our users that are located everywhere. The challenge, however, is that if one of the data centers happens to be unavailable when a write occurs in the system, we have to make two choices. The first is that we can remain consistent and block the write operation until all the data centers or a majority of data centers are online, which is referred to as CP in the CAP model. Or we can allow the local write to proceed at the data center that the write arrived at, and we can risk inconsistency between our replicas and reconcile it optionally later, which is the AP model in the CAP model. So one way of solving the challenge of inconsistency and reconciliation in the AP model is something that's referred to as conflict-free replicated data types. Conflict-free replicated data types are distributed data structures that mimic their sequential counterparts. So we can think of having a set that has normal sequential set semantics, however, also deals with the fact that operations will happen concurrently without coordination. The idea here is that concurrently, if operations are performed against the set, such as adds or removes at multiple data centers concurrently, then all of the replicas will merge to the same result without coordination and deterministically. These come in multiple flavors: state-based, delta-based, operation-based, and pure operation-based, and a variety of others. I'm going to talk about state-based CRDTs, which have been the most widely deployed variant of CRDTs for the moment. State-based CRDTs come in a number of different data structures. Counters, for instance, there's multiple variants of counters, such as a counter that can only grow or a counter that can grow and shrink. There are multiple variants of sets. There are sets that can only grow. There are sets where you can add and remove only once. There are sets where you can add and remove and re-add. There are sets that bias towards addition under concurrency, and there are sets that bias towards removal under concurrency, on which operation wins in the merge. With registers, there's also multiple variants of registers. There's a last writer wins register where a value is used to arbitrate which one is kept. This could be a physical clock, it could be a logical clock, it could be arbitration based on some other aspects such as the data center ID or the client ID. And there's multi-value registers, which are registers that can take on multiple values and then merge back to a single value. Finally, there's a bunch of variants of Booleans, which are referred to as flags. And there's an ever-growing number of sequences which have different merge strategies depending. So the challenge here is that if I have a register in memory and I concurrently write to that register at two different data centers, I have to deal with the fact that writing to a register doesn't commute. There's no way to make that operation commute. And similarly for a set, I also have this challenge. If one person is adding the element 1 to the set, while another person is removing the element 1 from the set, because one is already in the set, what should the outcome be? This does not necessarily commute. I can't reorder pairs of operations and get the same result. So to demonstrate how some of these merge strategies actually occur, I'm going to look at one specific type of CRDT called the observe remove set and talk about how it merges. So to start with, I'm going to have three replicas: data center A, data center B, and data center C. In each of the replicas, I'm going to model the set using a 3-tuple. So the 3-tuple is going to represent the first position of the tuple, which is the set 1, will represent the elements that are in the set. The second tuple will represent elements that have been added to the set with a unique token that's generated to represent that add. We'll call this lowercase a here just to signify it was A's addition, but this is a random token. And then finally, a set that captures the removes that have been issued to the set. So here, when A goes to add 1 to the set, it adds 1 to the set, it generates a unique token, lowercase a, and it says 1 was added because of it was added at logical time A. Now, if B is concurrently adding 1 to the set, it generates a different token to say that 1B is also in the set. So 1 is also in the set because of the addition at B, and 1 is in the set because of the addition at A. Now, when data center sends its update to data center A sends its update to data center B will take, out of those two subcomponents, will take the pairwise union of the elements. So we see here that now at data center B knows that 1 is in the set because it was added at logical time A and logical time B. And when A sends its update to C hasn't done any updates yet. It's starting with empty state. So it just accepts that update and says, okay, all I know is that 1's in the set because A added it. Similarly, when B sends its update to A, it merges and it arrives at the same result that B did. And this is important because this is the commutativity property that we're kind of encoding in the data structure. So A happened to B happened concurrently, but when they merged without coordination, they ended up with the same result. Now, when C goes to issue a remove, C can only remove what it's observed. And so here, C takes its additions and unions them into its removals. So we see now C says there are no elements in the set, because A was added at 1 was added at logical time A and also removed at logical time A. Now, when B's update eventually propagates to C and C's update propagates to A, they all end up with the same result without requiring coordination. However, at C, we see that 1 has now been resurrected in the set. And the reason is because C was only able to remove B's addition. C had never observed the addition by A. So C unions A's changes in, and now it says, okay, 1 is in the set because it was added at time A, added at time B, and removed at time A. And since our additions are a strict superset of our removals, then I know that 1 should still be in the set. And so we see the outcome after all of the convergence, 1 remains in the set. CRDTs have been put into production in a number of systems. The React distributed database was the first major production implementation of state-based CRDTs. React is used by NHS. The CRDTs are used on Riot Games, League of Legends, very popular game. They're used for betting management at Bet365 and William Hill in the UK. And in Latin America, they're used for vehicle recovery and telemetry information for LoJack. At HPTS 17, Antidote DB was presented. Antidote DB is a operation-based CRDT database that has a technique. It uses a technique called transactional causal consistency, in which the database provides causal consistency, transactions that use snapshot isolation that guarantees causal consistency of each snapshot, and also has operation-based CRDT, so transactions are mergeable and convergence is guaranteed. This is a research project that's in the process of being put into production. And then finally, a number of other systems use CRDTs, Mesosphere's DCOS, its internal databases, and Load Balancer, Lashup, and Minutemen, Adobe, Comcast, obviously ourselves, TomTom, Roshi from SoundCloud, AutoMerge, Ditto, Cosmos DB from Microsoft. There's a number of others that use all sorts of variants of CRDTs, mainly around the state-based variety. So what is Macrometa? So Macrometa is a document database for the edge. We can think of documents as JSON documents, similar to CouchDB, and documents are grouped into collections similar to something like MongoDB. So we can think of collections as namespaces, and documents basically are dictionaries that are presented through rich clients to the user in the kind of idiomatic way for the programming language for the client that they're using. It's located in 155 physical regions with 175 logical regions, because many physical regions have multiple fault zones, so those can be subdivided into additional regions that can be deployed into. 36 of these regions are reserved core. 12 of them are available through the public beta today. These reserved core regions are managed instances by Macrometa themselves. 34 of these are customer requested regions, such as on-prem or specific colo or similar to this. So customer requested, usually customers manage the facilities, for instance. And then 35 of these are on-demand activatable burstable regions. And this is because not all regions have the same cost profile or necessarily are available for all users or something like this. So these are regions that can be activated on demand if the customer requests them or are needed for availability or capacity reasons. Macrometa has configurable consistency, so it has strong consistency where writes are taken in a single DC, they're written in order, and propagation happens to remote DCs in the order that the writes are accepted and applied to the data store. It also operates in eventual consistency mode, which is a multi-master mode where all DCs receive updates and can apply them, and then the updates are propagated in causal order. We'll focus on eventual consistency, which is the more challenging component in this talk. So the architecture is basically a standard kind of database-based logging architecture. There's a cluster of bookkeeper nodes that are managed by Zookeeper for metadata management and membership. Bookkeeper is used to store the ledger. So there's a ledger that represents the writes coming into that log. Writes are durably written to a cluster of nodes to ensure durability and high availability. Then there's ledgers out to the remote data centers that are used to kind of write out buffers of logs that should be shipped out to the remote data center. Now these ledgers for the outgoing ledgers out to the remote DCs, the updates are sent in FIFO order, and when those updates are received at the remote data centers, they're buffered until dependencies are met. So each write includes the context of the writes that it observed before, so a visibility vector. And updates, when those updates are sent to the remote DC, those updates will not be applied to the remote DC until those dependencies are met. So if data center 1 is sending updates to data center 2, but 1's updates rely on some updated observed from 3, 2 won't apply 1's updates until 3's updates have been received. And then finally, clients operate at the document abstraction level, which means that clients basically, users interact with documents through their client. Those documents are then, when those documents are then sent to the remote data center for writing, those documents are diffed against the value in the current data center, and that produces a change set, and then that change set is sent over the wire. Now, those change sets are written to the log. When they're received on the wire, what we do is we rematerialize the values for every document in the database. So these things are materialized and cached. As updates come in, those caches are updated. So the writes are fast because they read from pre-materialized values, but we are using a traditional database style logging architecture. So some of the concerns we have to think about when deploying this architecture across multiple data centers is that our regions are federated kind of over existing infrastructure from cloud providers, and which means that all of the regions have different SLAs, they have different availability, they have different performance, and they have different costs, which kind of alludes to why some of the regions are activated on demand and not always live, and things like this. But more importantly, since we're using existing cloud provider infrastructure to run an overlay on top of, we're paying for storage on each provider, so it's very important that we minimize long-term storage costs on these providers to keep the cost down. So these two things kind of play into why we have to have a custom design for the way the data center stores and works with CRDTs that may be different than existing CRDT designs that we see in the literature. So let's talk a little bit about how the system works. So the system kind of originated with last writer wins registers. And so we'll kind of walk through an example of how this works, which will set the stage for the more complicated examples when we get to the richer data types. So for this example, I'm going to start with 3 data centers, data center A, data center B, and data center C. In each of the data centers, I'm going to use yellow to indicate a write that originated at that data center, and we'll see time moving to the right. So here, we're going to assume that we have a document that contains only a single register. And what we're going to do is we're going to set the value of that register. So here, what we're going to do is we're going to set the value of the register to Alice at data center A. And we're going to have a logical clock here that is sized on the number of data centers to represent the number of updates performed by each data center, and use that to uniquely identify a particular update in the system. So here we'll say that A has set the value to Alice, and the clock is now advanced to 100. So this update is designated by update 100. So A will propagate its update to data center C, but meanwhile, let's say data center B takes an update to another document and writes that to its log. So this just demonstrates that the logs are not totally ordered across all the nodes. These are partially ordered, so not all nodes will observe the log in the same total order, but they'll observe it in a compatible partial order that that is compatible with the partial orders of all the other nodes in the system. So then A propagates its update to B. Now, similarly, we have this other update propagate, but then A performs the second update where it changes Alice to April, and then that update begins propagating. So we see that DCB is delayed by an update, but data center A has now propagated its update to C. Similarly, B propagates its update to A. Now, when B has not observed the change of the register to April, so it sets the register to Bob and it advances its clock to 110. So we see that the update April is now concurrent with the update Bob at data center B. 110 is not comparable with 200, but we both know that these two updates supersede the update for Alice. Similarly, C can perform update before it sees B's, but after it's seen A's. So now C has an update that's not concurrent with A's change to April, but is concurrent with B's change to Bob. And this clock is designated by 201. So we know that 201 overrides 200 in the causal history, but we know that C is concurrent with B. So A is concurrent with B, C is concurrent with B, C supersedes A. So once all of the updates are in the system, what we have to do is we have to choose which value the system will converge to. And so what we're going to do is we're going to take all of the concurrent updates and we're going to pick the maximum data center identifier here, which is C. So A is concurrent with B and merges to B, and B is concurrent with C and merges to C's update. And so finally, at the end of the execution, the register is Charlie. Now, what this ensures is that at the end of convergence, we need only to keep a single update in the log for each field in the document. So here, I can throw away A's Alice update, A's April update, and B's Bob update, because we know that once everybody has observed the update for Charlie, it's safe to remove everything else, because we know the Charlie update overrides all the other values in the system. Now, the problem with this is that registers can end up giving user what we kind of can refer to as read anomalies, where users see unexpected behavior since the updates are sent independently, right? So we don't send the entire document, we send individual updates. And so because of this, we can demonstrate kind of a simple read anomaly that a user might exhibit using a similar example to what we had before. So if A sets the first name let's assume a document with a first name and last name, middle name, A will set the first name to be Andrew and propagate that update. So similar to the execution before, it looks very similar to the execution before, except instead of A changing the first name, A will then set the last name to Carnegie. So we can imagine this as in the client, the user does a series of modifications to the data structure, sets the first name to Andrew, sets the last name to Carnegie, and then propagation happens roughly the same as the propagation happened in the last example. However, if the user issues a read at data center B at this particular point in time, another user will observe the first name being set to Andrew and the last name being set to undefined, or the key not being present depending on your client. Now, this is a read anomaly if user A, the user writing to data center A, expected that Andrew and Carnegie will be read together atomically, because here they're only seeing part of the update. Now, typically the way you solve these types of anomalies is you use a transactional facility. So transactions typically provide many guarantees, but typical ACID transactions, the two most important guarantees are atomicity, which is that groups of updates are guaranteed to execute together, and then isolation, typically serializable isolation, where you guarantee that transactions that occur simultaneously, only one will win, and you'll have the appearance that it happens instantaneously. So concurrent transactions will be ordered, and they'll appear to happen instantaneously. So here we provide kind of a lightweight form of transactions to solve this problem, where we guarantee updates will occur together, and we don't apply them until we have the batch. Now, we apply that batch at anywhere in the order in the log, so we don't guarantee something as strong as serializability, but we do guarantee that you will not read kind of updates divisibly. So the updates will be indivisible. So if we have our example again with 3 data centers, we'll start by performing the updates where we'll change the first name to Andrew and the last name to Carnegie. And for the logical clock, we'll assign the same logical clock. So these updates will be grouped together with the same logical clock, indicating that they should be part of the same update. Now, as other updates occur in the system, we'll transmit these updates atomically together, and we'll apply them to the log at the exact same time and rematerialize the object at the same time. Now, what this guarantees is that any reads that happen to interleave will not interleave in between these sets of updates. So this is kind of the weak form of isolation that we provide, which guarantees that that you don't exhibit the read anomalies we had before. Now let's see how this works under concurrency. So under concurrency, we'll have the updates where Andrew and Carnegie will occur together, but we'll also have an update at data center B that will change a different field of the document. So here we'll set the death field to be 1919. So we see that the death field has the logical clock 010, and the first name and last name change are grouped together in a batch that has the change, the logical clock change identifier 100. So these are concurrent. So when these updates propagate, they'll propagate together, so we don't have the read anomaly we talked before. But how will the merge happen? And so when there's no conflicts in the document where two transactions haven't modified the same fields and those transactions are concurrent, what we'll do is we'll take the concurrent transactions and we'll merge them together. So in this case, since there are no conflicts, we end up with Andrew Carnegie 1919. However, if data center A had also changed the death date, B's change to the death date would win over A's because it would pick the maximum data center identifier per field in the document. However, this transactional facility also leads to anomalies. So since it's a weak form of isolation and not something as strong as serializability that would only take one set or the other set of updates, the anomaly that we can run into is that if B changes the last name to something like Brown, and these updates are propagated, so exactly the same propagation that we had before, we end up with Andrew Brown. So when the change is to the same field, we end up by picking the maximum data center identifier for each field, which is convergence by field, which ends up with Andrew Brown, where if it had been a change to a different field like the death date, we would have ended up with all the changes. And so this is because the isolation level is so weak and we merge concurrent transactions together. So we evolved this transactional system to provide something that's a bit more expected that users would expect. So something that's got a bit stronger guarantees. And so we see here that what we'll do instead is that if we have A and B, Andrew and Carnegie again, and we have similarly our concurrent update to Brown, we'll propagate this as normal, but when the merge happens, what we'll do is we'll take all of the concurrent updates from a single data center. And so in this case, we'll take either Brown, which is concurrent, so undefined Brown, or we'll take Andrew and Carnegie. It just will happen to pan out whether we've chosen from data center A or chosen from data center B. Now this is similar to a stronger form of isolation because we're only allowing one update out of all of the concurrent updates to win, and we're refusing the other ones or effectively rolling back their changes in favor of another. So this has become the new transaction mechanism, and the existing transaction mechanism has been renamed to atomics. So if you're not concerned with changes to multiple fields where you need to guarantee that all or none are taken, atomics basically uses the standard merge all the fields by fields. And this is similar to how transactional causal consistency and antidote works. It basically merges all of the concurrent fields and does not give you a granular option like this. So in their world, they have either strong consistency or atomics. And so our transactions kind of fit in the middle because it guarantees all or nothing without guaranteeing total order. So let's talk about counters. So counters have traditionally been very, very difficult to build in distributed systems, mainly because of the problem of reordering and duplication and dropping of messages. So the first problem with counters is that we can't model counters as a register where we set the value of the register to be a number. So read the value, set the value, and apply it, because assignment, as we said, doesn't commute. You can't assign to a register and have it commute without having an arbitration like maximum data center ID or physical clock or wall clock or logical clock. Now, the problem is we can't store the counters as registers at different replicas and then sum the values, because any counters that overlap, if one data center updates a counter and propagates it to another, and we just add them, we'll end up double counting. So if we sum the values across registers, we'll end up double counting. Where if we take the maximum, we can end up undercounting. So if two data centers increment once, they haven't propagated to one another, and we take the maximum, then we lose one of the updates. So sum double counts, max undercounts. And so this is kind of the problem. So there's two basic strategies. We can store a vector and store sums per node. So we can take the maximum for each node and store sum across of it. Or we can store the individual increment operations. So one is more space efficient, but the other works with other mechanisms, and we'll see what that means shortly. So CRDT counters come in roughly two flavors. So the first is state-based CRDTs. These are the CRDTs that are used by React, for instance. Now, to model a counter, what we do is we take a vector. The vector has n positions for n of the data centers that are in there. Each data center only increments its own position, and when merging takes the maximum. And then if we want to know what the value of the counter is, we take a sum across those positions. So everybody only modifies their own position. Now this is this data structure that I'm designing here refers to is a form of lattice, specifically a bounded joint semilattice. Now the storage overhead is very low. It's still large, but it's low because it's ordered only on the number of data centers in the system. However, it requires extremely careful design so that updates observe very particular mathematical properties and guarantee that things are always mergeable. Otherwise, you risk running into data loss. Now, a second variant is operation-based CRDTs, where these are optimized for individual operations, which means they're compatible with transactions. Now, with operation-based CRDTs, what you'll do is you'll store every increment to the counter as an individual record in the system. Each of these updates are designed in such a way that anything that can occur concurrently with them has to commute with them, but they don't need to form a lattice. All of these updates are stored, and then eventually you use a consensus-based garbage collection to know when everybody has seen a certain set of updates, and then you purge those updates. And also, since we're only looking at concurrency, at reordering between concurrent operations and not reordering across any operations, this requires causal broadcast to make that guarantee. And these are the type of counters that Antidote uses, for instance. And so the question is, how can we find something that is low in storage overhead, so state-based style storage overhead, that is also compatible with being able to be garbage collected and work with a transactional facility, which we just outlined in the previous section. So let's talk about why state-based counters don't work. So if we have data center A, B, and C again, I'm going to model my updates this way. So here I'm going to say A has incremented the counter at this time. I'll say that A has incremented the counter, and the counter's value is 100. Similarly, 700 represents the document clock we've had in all of our running examples so far. So this says that the document this is the 7th update to this document, for instance. So here, A updates its position of the vector to say that it has incremented the counter 1. So A's position goes to 1. And then if I want to know the current value of the counter, I sum across that vector so that the value of the counter is 1. So if I propagate that, propagation happens as normal, like we did in our previous examples. And then if A goes to update the counter a second time, it advances the document clock, and then it updates the clock of the counter. So we say the clock of the counter is now 2. A has done 2 increments. The total value of the counter is 2 plus 0 plus 0. It's 2. Now, if B goes to increment the counter before it's observed A's second update, the document will advance to 710. The counter clock will advance to 110. So if I take the sum of that, 1 plus 1 plus 0 is 2. The count of the value of the counter now at data center B is 2. So the total count at this point in time in the execution, the counter should have value 3. But A's seen 2 of its own updates, B's seen 1 of A's updates, and 1 of its own updates. So when A performs its final, so when the merge happens, when A sends its update to B, what we'll do is we'll merge that so that the counter ends up being 310, because now we take the maximum of A's position, which is 3, the maximum of B's position, which is 1, and now the counter is 4. So A has done 3 increments, B has done 1 increment, 310 adds to 4. The document clock is 910, representing 9 changes by data center A. We started with 7, and 1 change by data center B. So this is fine because everything merges to 4, and this is great. This is the desired result. This also means that I can kill any updates except for A's last update, because A's update includes everything it's already seen. So we only need to keep, in the ideal case, once propagation is completed, the final update in the system. This is also good because the storage overhead for the counter is just ordered on the number of nodes per counter. So the counter has size 3 and is 3 here because there are 3 data centers in the system. So why don't state-based CRDTs work with transactions? So if I was to have the exact same example that I had before, but each of these updates in the system were in individual transactions, what would happen is that this update, where B's update, where it increments the counter with clock 1, with counter clock 100, and A's update with the increment of 200, these two updates would be concurrent. And if all of these updates were performed in transactions, the transaction rules mean that I need to throw one of these updates away, and really I should be throwing A's update away. Now the problem is that if I've already collected all the garbage in the system, and I've only left with this final value where A is 310, which is 4, I have the wrong value in the system because I should be removing one of these updates. Now the way this would be solved in traditional database systems is that until I knew I had received all the concurrent updates from all the data centers, I would have kept all of these updates so I could roll all of them back and then reapply them. However, the problem here is that our updates for A have already been written to the log, and that log may have been already shipped to remote data centers. And so the undo log would have to undo all of the updates, rewrite all of the updates, send these updates to the remote data center so they can undo them and rewrite all of the updates. And so this doesn't work. However, again, the benefit of this approach is that the storage overhead is order n on the number of nodes or data centers per counter in the document. So let's look at operation-based. So operation-based we know are already compatible with transactions because they're used in systems like Antidote. And to make operation-based work, all I do is rather than store the clock representing the current value of the counter, I store individual increments to the counter. And so here it's the exact same example I had before, but instead of storing clocks, I'm storing just an entry in the log that says the counter has been incremented one time. Now at the end of the execution, I run into this problem where if everything is in the transaction, I have to throw one away. But that's okay, because when I actually materialize the objects that the user reads, I can just ignore the concurrent updates and I can ignore A's update and I end up with the right value. However, the challenge with this approach is that until I perform garbage collection, which requires consensus, my storage overhead is order n on the number of updates per counter. And so this is much more expensive than the one that's fixed on the data center size. And so the approach that we had to settle on is a hybrid approach that uses techniques from both state and operation-based, that uses an asynchronous garbage collection process where things are kind of pruned out of the system automatically. So we pay a bit more space overhead while the system is operating to kind of deal with updates that are occurring in the system. And then once concurrent updates settle, rather than using a consensus protocol, we just automatically convert to a more efficient representation on disk. So here what we do is we start off with data center A, data center B, and data center C. I'm going to store my increment documents in an operation-based way. So I'll say here that A is incremented once, and this is my document clock that shows 100. A will propagate its update, B is an update to an unrelated document. A updates its increment values again, it increments the counter to 2, it sends those updates along. Meanwhile, B increments the counter concurrently, and it then propagates those updates along. So here we have roughly the same execution we saw before, except we have a few more increments done by A. So at the end, we see that we've had 4 updates, 4 increments of the counter that were performed by A, and a single increment of the counter that was performed by B. Now what we're going to do is we're going to have a flexible time period that we're going to wait where we do not perform garbage collection. And then at the end of this period that we'll refer to as the moving convergence window, which you can imagine is 2 to 3 days or 24 hours, what we're going to do is we're going to create an entry in the log that summarizes all of the activity before the start of the window. And what we're going to say here is that A is incremented to up to logical time 200, and this summary is being put in the log at logical time 510. So the kind of document clock is 510. So what this update does is it captures all the updates from the origin update, the origin summary of 0, up to the start of the window, which is only 2 increments performed by A. Now, once this summary is written to the log, we can remove the garbage from the log that the summary captures. Now, once that garbage is removed from the log, then we can propagate that summary to the remote data centers. So the remote data centers will receive the summary, and when they receive the summary, they know that all of the updates for A that are prior to a particular logical clock can be removed from their logs as well, regardless of their position. Now, this process will be occurring while updates are still being taken at A. So A is still advancing in time and writes are still being performed. And as the convergence window advances, now B's update and A's update fall outside of this. And we run through this process again. And when B does this, B writes a summary entry into its log saying up to logical time 100, I performed 1 increment since my last summary. And then it will basically propagate that summary to the remote data centers and prune its own garbage. Now, when those remote data centers receive that update, they also can prune B's garbage. And what this involves is it allows us to asynchronously perform garbage collection without coordination, which is different than the traditional operation-based CRDT systems that use coordination for establishing a causal history frontier from which garbage can be pruned. And it also allows us to convert this to kind of a state-based representation that can be asynchronously broadcast to the systems, which also alleviates the need for consensus there as well. It allows us to keep the system moving while we're converting garbage. Now, the nice part about this is that it allows us to reduce storage costs, because long time storage costs go down because we don't have to store all the updates for something ever. Eventually, every counter gets reduced to order n on the number of data centers per counter for the summary objects. And it also allows us to basically leverage this conversion between operation-based for running while we need transactions and converting to state-based once we're outside of the window where concurrent operations can occur. So kind of the question I'll kind of leave you with at the end here is, are these actual CRDTs? Probably not. And the interesting discussion to have here is that CRDTs kind of guarantee this kind of permanent convergence guarantee, right? So a data center should be able to be offline for an indefinite, for an arbitrarily long amount of time, come back online, and then send its updates and merge in. And effectively, what we're saying is, with using that moving convergence window, we say that all of the concurrent operations you're going to see have happened in that window, and outside of that, we have to just ignore any updates that occur outside of that. So this requires setting this window to be fairly large, buying the buffered storage that's needed to handle the amount of updates that occur before the window, and then eventually evicting the node out of the cluster once the updates have taken too long to propagate. However, I do think this is quite an interesting point in the design space because it kind of fits halfway between React and Antidote. React took this extremely pessimistic model that was so pessimistic it was like nodes could go offline for a super long time and come back online, and we want to guarantee convergence, so we're going to put a lot of effort into data structure design, and we won't even try to think about causal delivery. Where Antidote is a much more optimistic system where it assumes causal broadcast is fine, we can use coordination whenever we need to perform metadata maintenance and things like this. And that nodes will not go offline indefinitely. And so I think this is kind of a very interesting, realistic point in the design space to show the trade-offs that you have to make to actually make some of these CRDTs work in the real world. Thank you.